So we did cover in the last lecture the various numerical demonstrations indicating or providing overwhelming numerical evidence that the approach is sound. Okay, so this is in light of the fact that in all likelihood you have not made use much of alchemical transformations yet, and that in all likelihood this is also a rather new concept to you. I hope that the last lecture convinced you that there's nothing wrong with this, right? That across, just as general as quantum mechanics, you can make use of this concept. Now, what you do with this is, of course, up to you, right? In particular, in the context of this course, we are interested in design. So we would be interested in exploiting this for gradient-based optimization of QM properties in chemical compound space, right? So this is an obvious application of this. And we discussed last time, it has been just mentioned as well in the summary, the description of the band structure of a material using these alchemical derivatives, right? Now, in this chapter, we still talk about our understanding of chemical compound space. So I have not included the results from that same paper where this was used to enable the computational design of new semiconductors, just in the same sense as in this seminal paper by Alex Zunger and Franceschetti in the Nature in 1999. So we will discuss this particular application then to design in our chapter on applications, okay? Now I'd like to continue to deepen a little bit our understanding of chemical compound space in this QM sense. We have basically, these are 2 or 3 papers that came out from my group over the last couple of years that in my humble opinion have shifted or increased our understanding quite substantially of the relationships in compound space with the help of these alchemical transforms. So let me share the slides now that we can discuss together these concepts. Oh, and before we get there, I'd like to still show one slide from the paper on the band structure. I'm not sure if we discussed this last week, so. I'm juggling multiple screens and windows, and are you seeing what I see? What do you see?
Just a white screen.
White screen, okay, that's not good. moving around the stop sharing. Now let's try this again. Is that better?
Yes, it's much better.
We see the slides, but not in the presenter mode yet.
Now it's perfect.
Thank you. All right. So this was the paper we discussed on the band structure of aluminum arsenide and gallium arsenide. And in the subsequent application then for design, we use these derivatives, and you see their performance demonstrated here in these two figures and on the scatter plot. We then use this to consider the solid liquid mixture. So we treat it as if it was a liquid. You could exchange the atoms, and we can consider these mixtures. Then these are all sorts of gallium aluminum arsenide mixtures, right? So we have a mole fraction between gallium and aluminum on the lattice, and we can play with that mole fraction. And for a large unit cell with a fixed mole fraction, we can also look at different populations on the various lattice sites for the given aluminum or gallium atoms. Now, we also looked at other materials and the predictive powers, and you see this in this here. So the color code is the error we make in the first order prediction for across the entire band structure for 3, 5, and 4, 4 semiconductors, right? So these are all in the diamond lattice, so this is all relevant. You see this little snapshot here from the corresponding block in the periodic table. This is all relevant, of course, to semiconductor technology. Now, what you see in the ground, in the bottom right-hand panel here, is a scatter plot of the predicted band gap, right? And you see that this prediction is actually quite decent. Right? We will come to this later, but for machine learning models to predict such band gaps with such accuracy is very difficult, okay, at the moment. More interestingly, maybe, and this relates to the discussion we've just had in the summary on the error in your first order prediction and how it translates to the difference in the electron density or the electronic structure, right? Or the volume of your atoms, right? You see something like this in this lower left-hand panel. This is the error, and it's now scattered versus the difference in electron density integrated. This is the norm of the electron density, right? If you kept just the difference, it would integrate to 0. But if you take the norm, you can collect all the differences in the electron density, and you see that the error is actually something like an upper bound, right? So if this number is large, right, it can be that the error is large too. However, if this number is small, your error typically will be small too. Okay, your error cannot be very large if this number is small. So this is an interesting finding, right? You could imagine, for instance, of course, this scatter plot requires now to know the electron density of target and initial structure. right, to evaluate this integral. But you could imagine using a proxy method, right, a very approximate, cheap method to estimate the x-axis, right, and that should tell you something about the uncertainty of your first order prediction. So also this figure, right, in combination with what you have seen for the trends and the predictive performance in the single, double, triple bonds, right? This is also completely in line with what you would expect from regular perturbation theory, right? And so also here we see reflected now the fact that we rely on proper physics for performing these, for making these predictions. Okay, we discussed these crystals, and I'd like to now catch up again with the homework assignment and then take it from there, right? So we had discussed this picture of chemical compound space, and in particular, we want to now come to two papers. One is this 2019 paper in the Journal of Physical Chemistry Letters with a collaborator of mine, Stan Fiers, and Samuel Chang, who was my PhD student. And then also Guido von Rudolph, who's giving the other course. We wrote a paper on what we call the alchemical perturbation density functional theory. So the generalization of a chemical compound space towards geometries that are not necessarily in the energy minimum. Okay, they can be also saddle point, they can be whatever in your potential energy hypersurface. So for any configuration, right? So for any set of coordinates, you denote it by R, capital R, and any chemical composition, so any stoichiometry here denoted by Z, the nuclear charge, the set of nuclear charges, and any number of electrons, right? So this is 3 n-dimensional, the R. The Z is n-dimensional, right? For every atom you have a Z, and any is just a scalar. Okay, for any such combination, a compound would be a point for which you can solve Schrödinger's equation, right? And so you have the entire electronic spectrum sitting on this point, right? You can imagine an energy diagram, and every solution to Schrödinger's equation from the spectrum with all its differences by quantized energy amounts lives on any such points, right? And as we have now made abundantly clear, the space is smooth in R and Z for any of these eigenvalues. Okay, so this is how perturbation theory works, right? It's one of the assumptions. Now, if you have some state crossing, right, then of course the state you're considering might change its index, right? But that is okay. If you develop your perturbations, you can also do this in excited states, and there's no fundamental problem here. All right, so here we give as an example, we'd like to consider now this homolytic bond, right, the N2 molecule. In nitrogen, in a nitrogen atom, you have 7 protons, right? So in total 14 protons, total 14 electrons in your system. And we discussed now the second order derivatives we could observe for such a system. And these derivatives can be formed, of course, with respect to any dimension. Right? So any degree of freedom can be considered here, notably all the nuclear charges, all the coordinates, and the number of electrons, right? So this is your generalized Hessian and chemical compound space here. And each of these blocks, right, they have very well-defined meaning. Some of those we discussed already within the molecular grand canonical ensemble DFT. And of course, our first reflex, right, when seeing such a matrix is to diagonalize it. And this is in complete analogy to the vibrational analysis people would usually do for molecules in the minimum, in the equilibrium minimum. And if you do this, then you would be looking basically at this block here. So the second order derivatives of energy with respect to nuclear coordinates. And the diagonalization gives you the vibrational eigenmodes. Okay, so the eigenvectors correspond to the vibrational modes, and this is really undergraduate textbook knowledge in physical chemistry. So we recover this, right? But it's more general than this. You also have, in particular, changes in the nuclear charge, right, to second order, where we have a Hessian now, and we can diagonalize this one too. Right? And then you get something which would be something like an alchemical normal mode. Right? So for the nuclei, right, you get something like 3n minus 6. So the 6 comes from 3 translational and 3 rotational degrees of freedom, which do not affect your vibrations, right? So the relevant degrees of freedom here are 3n minus 6 normal modes for vibrations. But of course, in absolute numbers, you also include those normal modes that come from translation and vibration. In the case of the nuclear charges, you don't have 3n, but n normal modes. Right? There's an n by n matrix, right? And then, of course, if you do this diagonalization, right, with this Hessian, right, the general form is always this one. And so you can also expand your energy then in these normal modes. But you could also look at normal modes of mixed second order derivatives. To the best of my knowledge, this, for instance, this alchemical force, the normal modes have not yet been studied. Okay, this could be quite interesting if you wanted to do a master or PhD, right? This is certainly worth a paper publication to study how this looks like. So if we look at the nuclear charges, we can in N2, right? We have two nuclear charges, and it turns out that one normal mode is the one depicted here as an x-axis. It's a normal mode where you increase one nuclear charge and you decrease the other. This is an isoelectronic change, right? And it would bring you from N2 to CO to BF and so on. Now, at some point, of course, all protons are on one atom and 0 on the other. Now, if you have 14 protons on one atom, you have silicon. You have the silicon atom. So that's the united atom limit, right? And one position left to silicon in the periodic table is aluminum. So that would be aluminum hydrogen. Aluminum hydride is right before the united atom. So this sort of inverted parabola, right, goes towards the silicon atom, right? That is going to be the one atom limit. You have on this additional axis here the interatomic distance, right? And so I should say in the z-axis here, this is the electronic energy. The nuclear repulsion has been removed to facilitate our analysis. The nuclear repulsion is simply the product of the two nuclear charges over the distance. And this is a trivial term we know exactly. So for our analysis, this is not very helpful. Okay. Of course, if you want to compare to experiments, you then still have to add that term always. Right? But we now want to consider the most tricky part of the energy, which is the electronic part. And so you see here in this axis also the interatomic distance. And now as you dissociate the two atoms, right, you of course recover the limit of the sum of the free atoms' energies, right? And you roughly, we discussed this already, roughly speaking, this is 1/2 Z to the 7/3. Okay. Now, as the atoms come together, they will, of course, at some point fuse. Right? And then you have the united atom again, which is silicon. So if you wish, the envelope at the end of for zero distance and for your delta Z, the delta and the nuclear charge between the two atoms being 14, right? This kind of envelope is always the silicon atom. And from there out emerges this shape, this kind of ridge here in the red. And now you see that this red part here, this is the homolytic case, the symmetric case. Right? And it's trivial that CO has to have the same energy as OC, just by rotational symmetry. This must be the case. And so this parabola must be perfectly symmetric. Right? And you can think of it, of course, roughly speaking, in this limit, right, for large distances, the decay is the exponent of your nuclear charge is so it's Z to the power of 7/3, right? Which is the same as Z to the power of 2.33, right? So it's not quadratically decaying, but in between quadratic and cubic, right? So that's the where you are in terms of nonlinear behavior for the dissociated free energy term, right? Of course, as you get into, so this is in Bohr, right? So roughly speaking, at 2 Bohr, you have the equilibrium distance of N2. So here, of course, the energy will not decay with the same power law as the free atoms, right? These are the interacting atoms, right? And we don't really have figured out yet the right behavior here. But I can tell you that we are currently in my group we have a very talented PhD student with whom we figured out an approximate variant of which is very decent, gives very decent estimates for covalent bonding with a very simple formula. Right? It's not as simple as Z to the 7/3, but it's not much more complicated either. And so we are very excited about this, but this paper is we are currently writing up. We have the results, but the writing takes some time. And so, hopefully if you monitor our group's output, you should be able to see such a paper come out, this paper to come out next year. We believe that this is very fundamental, and so this is very, very exciting to us. Now you see here a little inset which tells you the error you make if you predict the neighboring and the energy of the neighbor along this blue line, right? So you fix this the interatomic distance here, and you make alchemical predictions to the left or the right using second order, up to second order, right? And so if you do this on N2, if you predict left or right, you're making the same error. Okay. But if you sit on CO and you predict back to N2, you're making, roughly speaking, the same error as when predicting from N2 to CO. But as you predict BF, your error is actually larger. Now, why is that? It's because, roughly speaking, right, second order would be a quadratic estimate of your of the shape of your potential, right? Now, if you go back to the maximum, right, that's where you come closest to parabolic behavior. And so your quadratic estimate will work better as you predict towards the maximum, right? It will predict worse as you predict away from it, because that's where the nonlinear behavior, roughly speaking, z to the 7/3, right? That's not the same as 6/3, which would be 2 as an exponent, right? So that's where it kicks in more, and so your error going away from the symmetric compound will be worse. In other words, what this would suggest is that if you make alchemical predictions from a highly symmetric system to its neighbors, right, you would expect, in terms of second order predictions, you would expect better accuracy than from a highly non-symmetric case, right? So if you are free to pick your reference, let's say you have a fixed compute budget and you want to get as accurate estimates as possible given a set of reference compounds which you would like to pick, these results would suggest you should pick the most symmetric cases, right? They would also suggest that if you make predictions and your reference systems is not symmetric, then you can expect your predictions to be more accurate when your target is symmetric than when your target is less symmetric. Okay, so that's what you see in this little inset here, and we push it even further, right? Then here, if you sit on beryllium neon, you're actually changing the group. You go from P elements to S elements, right? For beryllium, you go from boron to beryllium. So the predictive power is deteriorates tremendously, right? Which is also again in line with what we expected here from this kind of figure, right? Your electron density will of course change dramatically as you go from P shell to S shell, right? And so you would expect your perturbation estimate to become much less accurate as you include such a change. Okay, are there any questions on this?
Yeah, maybe one thing. So when you extrapolate with second order, yes, you kind of implicitly basically kind of fit the parabola at your reference point and then kind of go along the parabola to go somewhere else.
Exactly.
Now I wonder, I mean, we know that the shape is not the parabola, right? We know that the shape is to a very high degree like 7/3. Yes. Why don't we fit basically linear plus change to the power of 7/3 instead, linear plus parabola?
It's a perfectly reasonable proposition. We haven't had the time and the people to do it.
Okay.
I would 100% expect that this should improve the predictive power, right? Now, it would be guaranteed to do so in the dissociated atom limit. So it could be very interesting to make that exponent for the bound atoms, to make that exponent a free parameter which you can optimize, right?
Sure. Mm-hmm.
It hasn't been studied yet, right?
Okay. Makes sense.
So you see these papers, they are from 2 years ago, from 1 year ago. This is all very, very new, right? Okay. So now we are looking at the actual normal modes of this alchemical matrix here. And as I told you before, there this axis here, our x-axis corresponds to one of the two normal modes we have in N2 for the nuclear charges, these alchemical normal modes. It's this normal mode here, right? And we depict the change in Z by the color, right? Either it's negative or positive. Now, if you increase your Z, we pick the blue color, and you see that there's another normal mode where you would change both nuclear charges in the same direction, right? So this means basically you're either inserting protons in both of them, or you're removing protons from both of them. Now that of course means that your charge neutrality, your number of electrons you presume to be constant, right? And so this means that you no longer have charge neutral compounds, right? But that's okay, right? Your nuclear charges are free, independent degrees of freedom. And so we can happily vary the charge of the system in this way. And if you do this on both nitrogen atoms, then you either get to O2 2 plus, right? Or to C2 2 minus, right? So that's quite clear. But you do have something in between where you only add one proton, right? And so there's an inner circle here where we changed the diameter, the radius of this circle. It's basically a change in dZ of 1, okay? And so you can imagine these NO plus or ON plus or CN minus, right? They would lie on this circle, but only as a linear combination of your two normal modes. And so what you see now is a map of compound space of this diatomic case with this fixed number of electrons, and for fixed geometry, you have a complete map of the corresponding compound space in terms of linear combinations of the two normal modes. Okay. So it takes a little bit the shape of a shell, right? The more you vary your Z's, the further you can go out in this shell. And at the center, you have the symmetric homolytic bond. Right? What you see in this upper block here is the complete Hessian, the generalized Hessian for N2. So this thing, I'm sorry, this is not a determinant. This is supposed to be somehow the bracket got killed here up here, but this is an ordinary bracket, right? So this is this bracket, right? For N2. And this is at a certain electronic level of theory. So we actually calculated these mixed derivatives, and on the diagonal you have the second order derivatives with respect to the same variable, right? So these two have to be the same, right, by symmetry, and also these two. This is basically what would enter your vibrational frequency. Now again, these are the electronic contributions. So you would have to add the second order derivative from the nuclear repulsion 2 here to get to the total energy second order derivative. And this is the HOMO eigenvalue, right? Some estimate thereof. Now you can diagonalize this thing, right? And then you get these numbers, right? And these would be the eigenvalues, right? So these are the normal modes, and these are the eigenvalues. So this was your homework to show that that the gradient, right, at this ridge, because it's a maximum, right, that this must be 0 for any change that would vary your DC, right? So any change in this dimension here. And truly for any diatomic, so if this was not N2, but H2, right, going towards helium, right, or if this was lithium 2, right, or whatever diatomic, it could be O2, it could be C2, it doesn't really matter. It could be iron 2, it could be cadmium 2, right? It doesn't matter. And it doesn't matter at which geometry, right? Because it's homolytic, it will be rich like this, and your alchemical first order derivative must be 0. Now, I'd like to take a little break now, and then after the break, discuss this homework in more detail. It's now 8:55, so maybe we can resume at 9:05. Would that be okay? All right. Okay, let's continue. So the homework can be done quite easily using the Hellman-Feynman derivative of the corresponding change. And we'll discuss this now in more detail. And in particular, we'll discuss the generalization of these Taylor expansions and how they relate to really an orbital-free density functional theory version, which you can apply throughout chemical compound space. Now, one of the key concepts in this is that we aim to treat changes in your energy. So we are not going after absolute energies, but rather the change with respect to some reference. Right? So this is the root it's due to the root in perturbation theory that you must always have a reference. And so it's always about these changes in the energy. Now, before we get to that though, let me still show you an illustration of a generalization of these normal modes towards systems with more than 2 atoms. Okay, and in particular, a highly symmetric molecule would be something like benzene, right? And so you can imagine doping benzene with boron and nitrogen. So the equivalent of this normal mode where you have charge neutrality, and you can consider these normal modes for benzene. And there are 6 carbon atoms, so these are the 6 normal modes. They're shown here as a diagram. And it's quite remarkable, they really look like the Huckel molecular orbitals, right? But they have a very different meaning, right? And it's only when you look on it like this that they look similar. If you turn the Huckel system orthogonal to the plane, then of course you have the P-shaped orbitals, right? While for these alchemical normal modes, these are just spheres, right? So it's not a P-shaped orbital. But in terms of nodal structure, this is exactly identical. Now, as we discussed before, right, you can express any compound then as a linear combination of such normal modes. And you see this now demonstrated for all possible BN-doped variants of benzene. You see them ordered here as a function of the electronic energy, right? So if you dope only once with the BN pair, you have 3 pairs here. If you dope thrice with the BN pair, you have these 3 guys here. And then you have, I think, 11 guys in the middle, where you doped only twice, right? So this is the number of possible compounds, of course, follows something like a binomial distribution in terms of what's possible in your dopants, right? And as you know, in this frequency distribution, you have the maximum number when you have the equal amounts of all components available, right? And if you add more BN pairs, then you don't have enough space for your carbon atoms. And if you have too few BN pairs, then you have too much space for your carbon atoms. So this is also what you would expect, right, in terms of frequency. You see also that the electronic energy, of course, is the more you have atoms with a higher nuclear charge, the lower the energy. Right? So the overall trend in this graphic also makes sense with the stoichiometry. You can now write down any target compound as a linear combination of these normal moles, and this is done here, right? So the size of the little spheres here amounts to the size of the coefficient in your linear combination of that normal mole. Okay, so you see that in these 6 dimensions, right? We can now express all the 17 molecules. Right? And up to second order, we can of course also estimate the energy, right, with the corresponding eigenvalues, and that's what you see here in terms of predicted number. So that's in blue, and the actual true numbers in orange here. And you see a perfect qualitative trend. Okay. Now the agreement is not very good. It just looks good because the scale is very, very large, right? This axis is in Hartree. So don't get fooled by the seemingly good agreement. The deviation is still quite substantial. This is not chemical accuracy, right? But it's also not off by the order of a bond energy, right? So it's quite a decent estimator. I think if I recall correctly, it's on the order of 10 to 20 kcal per mole. So. Now, if you look very closely, it looks as if some of these dope guys have the same energy. All right. So, for instance, let me find one. These 2 guys here. These 2 looks as if they have the same energy. Right? Also, these 2. And so this looks like a degeneracy in chemical compound space. Right? It's not obvious why they would be the same. Right? And we will come to this later. They actually must be the same for a very good reason. Now, you don't have...
But, excuse me, but when I look at it, right, in the graph, I mean, it's hard to see because the resolution is tough. But it seems like the prediction of second order is the same, but in fact, they're not, right? And there's also no good reason why they should be exactly the same.
Yes.
But so are they the same or are they different now?
So it's exactly as you said. They are the same up to second order, they are the same.
Okay, makes sense.
And we will discuss this later. We understand very well how they differ and why.
Cool.
By how much, right? So, but we come to that in a moment. Think as the same as you don't have to stop at diatomics. You can consider 6 atoms. You can consider much more atoms. So this is a coronine molecule. Right? There's a lot of symmetry, and we can write down all the alchemical normal moles. Right? And so what this means is, right, that the basis functions, if you think of these normal modes as basis functions in chemical compound space, there's only n such basis functions for your n atoms, right? So that's a very elegant way to expand an incredibly large number of possible mutants. The number of possible mutants for the coronine guys, it's incredible, right? It's a combinatorial explosion. But you can express it in, okay, so how many carbon atoms are there? 6 plus 6 is 12, plus 12, 24 carbon atoms, right? So it's a 24-dimensional basis. or 24 basis functions you have here. And you can express any mutant of these guys in just these 24 basis functions. Yeah. Now, how many are there? It's crazy. Here, we made a figure. There's for this benzochoronine, for this choronine, there's nearly there's 1.7 million possible mutants, right? We can estimate to second order their energy. That's what you see here in black. And that's this black line. That's the alchemical normal mode estimate. 1.7 mutants, 1.7 million mutants, using as a basis just these 24 basis functions. We checked this, so on a subset, I think 2,000 molecules or so we did with DFT, and that's what the red line is. It's a subsample. It's not, we don't have it for everyone. Of course, it's very expensive to do these. Each DFT calculations for those is multiple CPU hours. Right? So we didn't want to burn, I don't know, 10 million hours. Now the alchemical normal mode estimate is basically it's free, right? You half an hour on your laptop. What you can do then, of course, is you say, well, now you have a huge library of compounds, right? Where you have energies. What do you do with it? Well, the first thing to do is, of course, to look at the distribution. Right? What is the distribution law of the energy in compound space? We don't know this law. We don't know that the equivalent to Boltzmann's Boltzmann distributions in configuration spaces. We don't have that for nuclear charges in compound space. So here you have something like a first shot at something like that in terms of the dash, the connected lines here. This is the frequency analysis. So the upper x-axis gives you the number of compounds per energy interval. So we selected some small energy interval, and then you can record how many compounds you have, and you see these steps here in the ascending cumulative energy distribution. You see these steps, they manifest themselves as peaks, right? So these plateaus then show up like this, and that makes a lot of sense. But it becomes obvious, right, that we don't have some simple unimodal distribution in chemical compound space. Chemical compound space is the superposition of many such modes. We can roughly link these peaks to different stoichiometries, right? So for a certain amount of BN doping, for very little amount of BN doping, you're up here. The more BN doping you do, you go down. So these peaks basically correspond to different stoichiometries. So the stoichiometries make you jump into a new mode, and there's a natural separation of scales, which you can see. It's not perfect, right? There is some overlap between these modes. So it's not an obvious thing. The degree to which you have overlap, right? How far each mode goes at most into the next mode, all of this has not yet been analyzed in much more detail. There's also something regarding our design problem which we should note. You see this energy region, let's say between -10 and -15, a hard tree, right? That's a huge energy window. You have a nearly constant slope, right? Very high density of compounds. However, so this is a high density region, right? But within this, these stoichiometries we considered within this molecular class, you do have a global minimum, just down here, minus 25. And there's nothing beyond that. Right? So chemical space is empty. If you go into a window region, an energy region where which exceeds minus 25, right? Or which is below minus, what is this, minus 2 Hartree, right? You will not find anything in this compound class, right? And then within that window, right, your distribution looks like this spiky thing. So quite weird. Okay. Of course, you could consider other compound classes, right? Other scaffolds, other stoichiometries, and so on. And then these distributions would be shifted. So it should be clear that under certain constraints, and usually in life we do have such constraints from experiments or whatever. We can encounter extreme scarcity in compound space. So despite its overall size, seemingly infinite for all intents and purposes, we do have a lot of scarcity. All right, now we did this for diatomics, for benzene, for these coronenes. This is now the same thing for solids. Okay, it also works for solids. The way we did this, and this is an extension, right? Now we include in the normal mode variables not only our nuclear charge Z, but also the row in which we are. We can do this by mapping the row and column information onto pseudopotential parameters. And then we build a Hessian in the pseudopotential parameters, either getting us up or down the column or left or right. Okay. And so then we can construct normal modes, which for a unit cell with just 2 atoms, so these are hexagonal unit cells with just 2 atoms, and we take 2 germanium atoms as a reference, and we have these normal modes, right? So this is 1, 2, 3, 4, 5, 6. Actually, it's really it's just like in the diatomic, only it's in periodic boundary conditions. But now we can go up and down, right? And so it's not really 2 normal modes, but there's really one where you go up with both, right? And there's one where you go up and down with both, right? And so this is either this brings you to silicon, right? If you go up with both, or to tin, right? That's the same normal mode, or left and right, right? So you get to gallium arsenide. So it's really this normal mode and this normal mode. And then you can have linear combinations again of either one of them or both of them. And that will get you towards any combination of diatomics in this 3x3 matrix. Okay. So by this, you can also see we can easily extend our alchemical normal modes to work not only in Z, but actually in any other measure of chemical compound space, right? It's more general than Z, right? So it's really just a lambda coupling parameter, which you can exploit. And so this is what you see here. And now what do you have in the main graph? It's a scatter plot, second order estimates, according to these normal modes, starting from germanium. We always use germanium, and we predict all these other materials. There's an estimate of the formation energy, the true energy versus the estimate, and in black you have the second order estimate, in gray you have the first order estimate. Okay. So you see on average a dramatic improvement when going from first to second order. You see, for instance, here the diamonds in first order, and then in second order they approach the diagonal much more. And these diamonds correspond to indium phosphide. Okay.
Quick question on the previous slide. So there were multiple crystal structures for each stoichiometry, or why do we have symbols multiple times?
Yes, so these are lattice scans. Okay, so we did this for different lattice scans, and you can see independent of lattice scan, you also have sort of a linear shift then, which so if you did two such lattices, right, you could have a correction, a linear correction, which then would move your entire lattice scan to very accurate numbers, if you wished.
Okay, makes sense.
Good point. And so, but what this I'm trying to show you also, right? There's a lot of structure which we can see, or which emerges as we apply this kind of analysis to compound space. And this is part of this 2019 paper. Nothing like that has ever been done before in the literature. All right.
Excuse me, I have another question maybe. Now, when I kind of compare to like 2 weeks ago the lecture, basically kind of one takeaway was, well, it's relatively easy to predict between third and fourth row, and it's hard to predict second row. And we had this argument of like atom radius and atom sizes.
Yeah.
So when I look at it and you start from germanium, I would have expected that it works well going kind of down towards like indium, tin, but it would be hard to go up, silicon, aluminum. But when I look at the plot, it's kind of reversed.
Yeah, so there's a trick here. We skipped the second row. There's no carbon in here. Right? We skipped the carbon. Right, nasty trick.
So it's like third row down.
We went directly to third, fourth, and fifth row.
Okay.
Also, partially because of these results you just mentioned. Right? We knew already that the predictive power would be worse, and we wanted, so we picked germanium as a reference rather than silicon, right? For that purpose, because we wanted to see how well it does, right? I would completely agree with you. If you did the same 3x3 matrix with silicon in the center, using silicon as a reference, you would expect worse predictive power than for predictions of the second row materials.
And maybe one last question, then I'm done with this plot. But so, like, again, like 2 weeks ago, the conclusion was, well, in many cases, first order extrapolation worked just as well, if not better, than second order. And here, I mean, it's not totally conclusive, but it seems very much that second order outperforms first order.
Yes. Yeah.
Why, like, is there some explanation why this would work better here compared to other systems?
So, yes, so we would actually expect that, so this is my speculation now, right? I would expect this to be related to the fact that here we really deal with solids and periodic boundary conditions. It's highly regular, right? While in the previous case we discussed, these were results for covalent bonds of small molecules saturated with hydrogens, right? Mm-hmm. So the effect of the finiteness of the system and the effect of these hydrogens intervening might play a non-negligible role when analyzing these trends. So this is what I would expect, but there could be other reasons at this. So it's yeah, to some extent you see the intuition as to why we observe certain things is rather shallow. There's not much we can say beyond. One could, of course, devote time to analyze this in more detail and try to develop a better intuition. But then again, all these papers have appeared just now, so this hasn't happened yet. All right, so let me now go towards this next paper I mentioned, this alchemical perturbation density functional theory. And this is really related to what we discussed, the Hellmann-Feynman derivative, which you see written out here, for the alchemical change, as I introduced this in a JCP in 2009, I believe. And so we can go from any compound to any other, and for now we just consider isoelectronic cases. And we plug this into this relative energy formula, which is just the for a conservative state function, right? We know that your integral over the derivative will give you the energy difference, right? And so if you insert your Hellmann-Feynman derivative and you change the order of differentiation, you find actually that you have here the difference in the external potential of these two multiplied with the lambda integral over the electron density. So this is really, at every point in space, you have to do this integration over lambda. And so this is some effective electron density, really, right? It's on average electron density. It's the average electron density over your lambda change, right? So you're averaging the electronic structure. So this is an incredibly powerful way of viewing things, right? Let me restate this. The energy difference between two systems is a functional, it's an integral over space of the difference in the external potential multiplied with the averaged electron density. That's what this is. Now, the average is not just the linear average, but the integral, so the integrated electron density average, right? Now, let's connect this to the Taylor expansion, which we use in perturbation theory, right? We write our target energy as this derivative, and so the zeroth order term is our reference energy. So this is the same reference energy as this one, right? So the right-hand integral here is the same as this Taylor expansion here, starting with n equals 1. Now, from Hellmann-Feynman, then you can see that your derivative here must be the derivative of the electron density multiplied with the delta V, right? And it's shifted, the index is shifted by 1, right? So your nth order in the energy is the n-1 order in the electron density. So this means we can pull the reference energy from the right here over, and we can insert this Hellmann-Feynman derivative, and your energy difference looks like this, right? And then you change again the order of differentiation. So you have a dr delta V, right, from here, times this summation over your Taylor expansion, right? And now compare this integral with this integral. Right? You have the dr delta V, and this is the integral over delta lambda. And this means that this lambda integral is nothing else than our Taylor expansion and the shifted index for rho. And this is what we call the rho tilde. This is our average electron density. So in terms of a reference, if you have your reference electron density and you can Taylor expand it like this, you can plug this reference electron density into this formula, into your Taylor expansion here, and you can then estimate the energy difference between the two systems. And this means that if you know your energy, let's say from coupled cluster or whatever, and you have a good grab on its electron density and its perturbations, then you can calculate the target energy to the degree that your Taylor expansion converges. You do not need orbitals. You do not need electron correlation. You don't need any such thing, right? You have, if your Taylor expansion converges, you have the exact energy functional of your target system. Now, of course, what you need here are the perturbations in the electron density. Similarly, since not only the energy is a state function, but also the electron density, you can also Taylor expand your electron density around your reference, right? And you can reconstruct the electron density of your target. Right? So in other words, if you have these derivatives, you get the energy of your target and the electron density of your target. And hence you have a density functional field. They're both consistent with each other. So as we go to a higher order, of course, the question is, do things converge, right? And here you have a first figure where we push this up to 6th order, actually, in the perturbation. And this is estimating helium from the hydrogen molecule, right? So the reference system is H2 at 1 angstrom distance. You see this here for lambda equals 0, you see the cartoon of the electron density, and we are predicting helium as shown here for the dash form, right? And we use now not DFT anymore, but coupled cluster single double as a reference, but we also compare to DFT and Hartree-Fock to see how the convergence behaves as a function of your density functional approximation. The most trustworthy number is this coupled cluster single double. And you can see now that using this formula, right, for your energy of helium, as you go to 5th order, you are, in terms of milli-Hartree here, you're practically exact. Right? What you also see is the same prediction for going from 1st to 2nd and 3rd to 4th, right? And 5th to 6th, right? So always the even order seems to be the same. We will come back to that later, right? So depending on the order and the symmetry of your reference system, you can observe such behavior here. What you also see is that these DFT functionals, PBE and PBE0, they somehow give you spuriously a better estimate for 3rd and 4th order than coupled cluster. Okay, but that's of course a better estimate of the DFT number, right? Which might be wrong by itself, but in terms of convergence, they seem to converge faster. We don't know why, right? We don't know. We don't know anything. So it could be that including such convergence behavior in the construction of your density functionals might be helpful to improve the overall accuracy of your functionals. You also note that the 1st and 2nd order, they are actually worse than coupled cluster. Okay. So it looks a little bit as if the whole curve is shifted downward. Maybe there's something one could correct like this, so that your DFT estimate actually is closer to coupled cluster than, or in absolute numbers, more correct than it would be. Right? Now, here you see predictions of binding curves of the CO potential. So basically, for the CO line, we are predicting this line using different density functionals. You see the alchemical estimates are shown by the symbols, right? And the lines are the reference, the true references. And these are just second order estimates. And you see that in second order estimates, as we knew already before from the single, double, triple bond scans, right? You get very decent estimates. The coupled cluster, this is particularly also true for the coupled cluster curve, right? So for instance, if you look at the Hartree-Fock curve, you still see some deviation between the alchemical estimate and the reference, right? But for coupled cluster, there's hardly any deviation in this binding curve. On the right-hand side, you see also the first time we've looked at large and small basis set sizes. So S is small and L is large. And you see the basis set size effect. And in particular, as a function of the distance, you see for larger distances, the basis set size in your alchemical estimate matters. For coupled cluster, it comes down a little bit. The zero is the truth, right? So this would be the perfect method. For these other methods, right, if you have mean field DFT or Hartree-Fock methods, a small basis set would overestimate things, a large basis set would underestimate things. Right? So you could compensate possibly errors of your functionals again using a certain basis set size, and this is also in line with historical development of DFT. For quite some time, people have been doing this, trying to fix density functional errors by using certain basis set sizes, so you get some spurious cancellation of errors or fortuitous cancellation of errors. With this, I'd like to now look with you at the electron densities. Okay, what you see here now are different molecules. So the molecules are shown here on the right. This is N2, this row. This row is CO. This is again CO. This is BF. And this is BF, right? And this sequence of molecules, as you hopefully remember, corresponds to this one, right? N2, we go from N2 to CO or from N2 to BF. So we are using N2 as a reference now. And you see here, all calculations are done with CCSD. You see here the N2, the equilibrium electron density of N2 with CCSD. Okay. On the right, you see the first order perturbation of your electron density. Then second order, third order, and fourth order. Right? These are the kind of electron densities you would use, for instance, in H2 to predict helium then. Right? So that's how they look like. In the case of N2, more specifically, if we sum them up, right? Remember this equation here. We get the rho tilde from our lambda integration, this guy, right? This integral. Right? That's the sum over these perturbed electron densities, right? That's our rho tilde. And so this is what you see in this left-hand corner here. This is the rho tilde summing up these electron densities, going along this one normal mode where one nuclear charge goes up and one goes down. That's the perturbation, the variable with respect you're perturbing here. Now, we repeat this for CO, and no, I'm sorry, we are not repeating this for CO, we are now predicting CO, okay? So what you have here now is the prediction of the electron density of CO using this electron density, the 0th order electron density. Now, this does not contain any information. It is the first order energy prediction. It doesn't contain any information of the electron density change with respect to CO. So the electron density is strictly the same. Okay, but now you're adding the first order term to this unperturbed density, and then you get the electron density of CO to first order. You're predicting it to second order, and you can hardly see the difference as you go from first to second to third, right, to fourth. They all already at first order, and the electron density, it's difficult to distinguish this by naked eye. The actual true coupled cluster single double density of CO is shown here, right? So this is the truth, and you're comparing all these estimated densities to this one, and you see it's hardly distinguishable. Now, one important thing, of course, which you can do with the electron density is look at the electrostatics that results from this, right? So what is the electrostatic? If you use that electron density and you calculate the electrostatic potential, this is what would then act on other materials or charges and so on, right? And that's what you see here. Using this predicted density, you see the corresponding electrostatic potential of CO, and here you see the true coupled cluster electrostatic potential in CO. And you see that also here, as you would expect from a hardly distinguishable electron density, also here the electrostatic potential is virtually the same. So you would expect the correct prediction of dipole moments, multipole moments, and so on. Now we can push this one further, right? For a larger perturbation, we don't stop at CO, but we go all the way to BF, starting from N2. Then for N2, nothing changes, but for BF, you see now, this the 0th order density would be like N2. Then first order, now you see a blob showing up here, which is spurious. In second order, the blob is gone. In third order, it shows up again, but further away from your nuclei. And in fourth order, it's gone again. Here's the true electron density of BF. And you can tell the difference to the second order, right? By visual inspection, it looks different. But if you compare it to the fourth order, you cannot tell the difference again. And the same holds for the electrostatic potential. If you build an electrostatic potential, right, for lower orders, it looks very different. And what you see then here is that the fourth order electron density creates an electrostatic potential, which is still distinguishable by naked eye from the truth, right? So the electrostatic potential is more sensitive to small differences in the electron densities. These two, the fourth order density and the true density, are not exactly the same. And so this pops up in this electrostatic potential. And in a qualitative way, right? Here you see the blue is a different color, right? So again, this raises then the question, how far can we go in this Taylor expansion? How quickly does it converge, depending on the extent to which you perturb it? So here you see some tables with integrated numbers, such as dipole moment changes and quadrupole moment changes, and also changes in the forces, which of course, due to Hermann-Feynman, the better your density estimate, the better your force. So we can compare all these numbers and see how they converge. And for N2 to CO, you see a very good alchemical prediction. So the error is shown here in percentage. It's this delta thing. And so you see here, this is 0.1 per mil, right? And the quadrupole moment is on the order of 0.2 on the order of 2 per mil. But this also depends on the interatomic distance. So we did this once for 1.1 angstrom and once for 1.5 angstrom. And you see that the error at 1.5 angstrom at the highest order is larger than at 1.1 angstrom. And so this is something one has to consider, right? That the error also depends on the geometry of your reference. And we would see that in vicinity to the equilibrium distance, you have more electron overlap. So given your basis functions, which typically account better for the equilibrium situation, you would expect the smallest errors for the equilibrium kind of geometries. And as you dissociate things, which is extremely relevant, let's say for transition states in chemical reactions, your error actually increases as you do alchemical changes. All right. I'd like, how is everyone feeling? Should we take a break or should we just continue and end earlier? Is there preference?
I would prefer to continue, but I mean, both is fine.
Okay. The others probably left.
For me, we can
already.
too.
What? Come again?
We can continue for me too.
Okay. Let's just do this. So in this next paper, I'd like to highlight a new or a separate aspect how we can use these alchemical changes to better understand chemical compound space. So as we just discussed, right, you can write the energy difference as this integral over the derivative, and this is the Hermann-Feynman derivative. It's only your electron, if you interpolate linearly, of course, then it's only the electron density, which depends on lambda. And you can then also use the chain rule to quantify the contributions which come from each atom that is involved in the change, right? So this is basically the chain rule going from dE to d lambda. You say now this is the sum over dE dz and times dz d lambda, and dz d lambda is simply delta z if you interpolate linearly. So you can pull it out in front of the integral, and you just have to integrate over the sum of these atoms. Okay. Now we know this derivative. This alchemical potential, which we discussed earlier, right? So this is akin to the electrostatic potential for the electron density. We are focusing here mostly on the electronic energy because that's the tricky part. And so we can use this, and now only the electron density depends on this lambda. So this means we can change order of differentiation, and we have our rho tilde again in the numerator. And so this is something like an effective alchemical potential, the average alchemical potential of your change. And that is then what we would call mu I, right? And so we have now partitioned our energy change into atomic energy changes, right? For each atom in your system, you have a well-defined change in the energy. So the math is very clear here. It's very easy and straightforward, just a combination of chain rules and substitution. Now we can do the same for the electron density, right? You write your change in electron density as the same here, and then you use the chain rule, and then you get contributions to changes in the electron density from each atom. Now you might be aware of this or not, but there has been this is a long-standing quest for chemists to understand or to partition the total energy onto certain parts of your molecule, right? We all love to think of chemistry in terms of Lego blocks, which we can exchange and rearrange. And so we would love to see, to know how much any given functional group would affect your energy, or how much it would affect your electron density. And this is precisely what the formalism allows you to do. But as you might know, there's a certain arbitrariness in how you can do this, right? So your energy is a global quantity, and so there's many different ways of writing this global quantity as a sum of its parts, right? So this is a partitioning problem again. We discussed integer partitioning problems for nuclear charges, and now you have a fractional partitioning problem. So you have a continuum of possible solutions that would all sum up to the same energy. Now also the electron density is a global solution, so you can, everything I just said for energy also applies to the electron density. Now, this arbitrariness is easy to show if we take a molecule which is inspired by benzene. We basically collapsed all the hydrogens into the carbons, and then you have 6 nitrogens in a ring. Okay, this is perfectly fine. Electronically, it's a fine molecule, right? Chemically, in reality, might be difficult to synthesize, but this molecule happily lives in the minimum, and we can now use these formulas we just discussed to calculate the energy contributions of each atom towards the total energy contribution, towards the total change in energy as you go from this molecule to the left to the right-hand side, the hydroborazine molecule, right, which is the fully BN-doped benzene mutant, if you wish, right? And so what you see then is, most notably, that those atoms which did not change their nuclear charge, right, they do not contribute to the change in the energy by this formula. If you look at this formula here, it's your chemical potential is multiplied by delta Z. So whatever atom does not change in its nuclear charge, it will not contribute to the energy difference. Okay. So these nitrogen atoms contribute 0. The hydrogens attached to the nitrogens, they are changing, right? They grow out of nothing here. So this is a big change in energy. It's slightly different than the hydrogens growing next to boron, right? Of course, the electron density environment is different. So there's mu tilde, their chemical potential, the average chemical potential is different. So they will not contribute by the same amount, something we find reasonable, right? They have different chemical environments, these atoms, so these hydrogens should not contribute by the same amount. And the borons, of course, there's a dramatic change from nitrogen to boron. You're removing 2 protons. It's basically these 2 protons form the 2 new hydrogens, right? So there's a dramatic change in the energy with opposite sign, right? So positive sign. And so you get this for all these atoms, right? And in the total sum of all these changes amounts exactly to the energy difference between these 2 molecules. But we have something irritating here, that the nitrogen atoms don't contribute anything to it. Now, things get even more weird if you consider the following path, where you change your nitrogens into the benzene molecule. This is an isoelectronic change. Every nitrogen now changes into carbon, right? So they all contribute, and we grow 6 hydrogens, and these are degenerate, these are symmetrical, so they always contribute the same. And then from this benzene molecule, we go again to the same molecule as down here, to the borazine molecule. But now our carbons are changing to nitrogen. And so now the nitrogens contribute an energy contribution of 0.016 Hartree. The borons contribute 49.391 Hartree as opposed to 49.381 Hartree in this case, right? And your hydrogens are the same as in benzene. So they all have this energy contribution, the minus 10.235, independent of being attached to a boron or nitrogen. Right? And so we get different atomic energies if we take this path or that path. And that is, of course, due to the fact that in your lambda integration here, things depend on how you choose your path, right? If you change your Hamiltonian in one way, your electron density will vary differently as you integrate and average over it. And so you will get different partitionings onto the atoms. The total energy difference between this guy and the borazine molecules is always the same, right? They different ways of partitioning the same energy difference. Right? And so this points towards the arbitrariness of these atomic partitioning of energies or electron densities. You can make the same argument. And so this is, it's not wrong, right? But it's not a uniquely defined property. Right? And comparing these partition properties is questionable. You cannot really establish global trends because they are arbitrary. Right? Now, it's important, of course, to distinguish. Just because they are arbitrary doesn't mean that they are meaningless or that they are wrong or useless, but it means we could possibly still turn them into something more useful if we had a single way to define them across all of chemical compound space. And this is what we have put forward in this paper. You can think of a global reference system, so not just this N6, but something like the uniform electron gas, from which you grow all atoms, right? And so if you do this, and you do it in the same way, that is through linear interpolation, then you get a unique partitioning of contributions, where then you can compare the atomic properties of very different molecules in a consistent fashion. So this is what we've been developing here, or proposing in this paper. And so you can see how this works. For instance, for N2, you see in blue here the uniform electron gas. And then as lambda increases, we slowly build up the electron density in N2. The same way we do this for CO, right? And then we can compare the CO, the atomic energies of carbon and oxygen in CO, right, as you grow your CO molecules. And now we have a partitioning of the energy contributions of the two atoms. And in CO, the carbon atom contributes a different amount of energy than the oxygen. So this is very intuitive and very much as we would hope for something meaningful. Again, it's not a general, there's no operator for this, right? So there are arbitrarily many ways of decompositioning this, but we would argue that this is a useful partitioning that emerges naturally from this these alchemical transforms. Similarly for N2, because of the symmetry, for instance, we get exactly the same energy contribution. Now here you can look at these contributions as a function of interatomic distance. This is the electronic energy, the total energy. And we can also compare this partitioning using, for instance, electron orbital overlap in a conventional setting, and you see you get very different partitioning, right? So what you're seeing here is the energy of each atom. This is the boron atom in the BF molecule, right? The boron atom in the BF molecule has this kind of binding curve. If you calculate the boron atom's energy contribution by using the orbital overlap from the MRCC code, your shape looks like this, right? The fluorine energy, it looks like this. And so the two together form a binding potential of BF. But in the alchemical partitioning, you get a binding potential for both atoms. The same is true for CO, right? You get a binding potential for carbon and for oxygen. And here in the MRCC code, you get this funny shaped thing. And here you have a binding potential as well. So it is the question, right? What is more physical? What is more helpful for interpretation? We think that this is quite interesting. You can also look at individual atomic contribution as a function of changing the bond order and so on, and compare this, and there's some interesting analysis here. Now I'd like to come on the last sub chapter in today's lecture, which is the alchemical chirality. And this is related to these dope benzene molecules having a similar energy in our normal mode expansion. So what you see here in our energy difference are these perturbations in the electron density. And we can look at these cases where to second order we had degenerate estimates, right? And so we go from this carbon to B and N on different atoms. And so if we take benzene as a reference, we can now apply a change, a perturbing potential where 2 carbons become nitrogen and 2 become boron, right? And this would be your perturbing potential then. And so this is the first order derivative. And these are the higher order derivatives. Now, if I apply the opposite potential, right, I just change the sign of my delta V, it looks like this, and it brings me to this molecule. Right? And the perturbed electron density actually looks the same except for the sign. And this tells you that if this is the same derivative, right, with opposite sign, it means that the energy difference here would also have the opposite sign, would have the same magnitude. This integral has the same magnitude up to the second order energy estimate. But it has the opposite sign, but I have another opposite sign due to my perturbing Hamiltonian going in the other direction. So I have minus times minus. And so these estimates actually, because it goes in the other direction, right? They have the same, you're predicting the same energy difference up to second order. If you look at the higher order derivatives, the third order is actually the same, right? So this is the second order electron density. Again, it looks the same. And these two, because you have an opposite potential, the contribution, the difference in the contribution of these two cancel exactly. So the estimate of these two benzene mutants, these two compounds here, is exact, actually up to third order, because the third order cancels practically. And so the higher orders, then you see again, very similar. These would contribute by the same amount, very similar, contributing by opposite amounts, and so on and so forth. So what you see here then is a kind of mirror plane in the perturbation of your Hamiltonian. So either you go towards this or towards the opposite sign, right? So if benzene is on this reflection plane, you either perturb to this molecule or to the one behind the plane. And so this is what we would call an alchemical chirality. And in comparison to a spatial reflection plane where you would go from this molecule to that one, this results in two mirror images which you cannot simply superimpose through rotation and translation. And so this is then what we call chiral, right? So this is the definition of chirality. And that's why we have a new symmetry, if you wish, which is a symmetry really an exact symmetry in your perturbing Hamiltonian. And in terms of your quantum mechanical expectation value, it then becomes a broken symmetry. It's exact up to third order only. Now, there's an interesting direct conclusion or consequence of the symmetry. If you start counting the bonds which you have, then you will see that in this molecule, you have a nitrogen-nitrogen bond, two boron-carbon bonds, one carbon-carbon, and two nitrogen-boron bonds. By contrast, in this molecule here, you have a boron-boron bond and two nitrogen-carbon bonds, and then also a CC and a 2NB bond. Okay? So this means there's something like a constraint on what's possible in terms of bonding between these very different bonds, right? In particular, if you approximately equate these two, then the CC2NB cancels, and you find that one NN bond and two BC bonds must, roughly speaking, be the same as one BB bond and two NC bonds. Now, this is very interesting because this means, right, bonds between the same atoms, you only for n possible chemical elements, right? You only have n homolytic bonds, right? But you have n squared heterolytic bonds. And so you could predict a heterolytic bond here if you know all the homolytic bonds and one other heterolytic bond, right? That's what this implies. And so this is what you see in this formula, right? So if you have three chemical elements adjacent in the periodic table, Q, R, and S, then the bond between S and R, so nitrogen and carbon, let's say, is, roughly speaking, up to third order, the same as the bond between Q and R, so B and C, plus half the difference in the homolytic bonds. Okay. So this is a new constraint on chemical bonding, which hasn't been described before in the literature. And in this paper, we also looked at this trend, how well it does for a whole bunch of diatomics. So you see here single bonds between all possible molecules. This is saturated then with hydrogens. And you always need three bonds. You need the homolytic bond, so shown here on the diagonal, CC and OO, to predict the CN bond, and you also need the NO bond, right? So two homolytic bonds plus one heterolytic gives you the third, the second heterolytic bond for free. Right? So, and you see here a scatter plot of the actual bond energies and the predicted bond energies using this formula here, and you see very decent correlation. The errors are typically on the order of the density functional approximation. So it can be even less than 10 kcal. And so this is a symmetry, a new symmetry in chemical compound space. It's also shown here once more. It's not restricted to these planar systems, of course. So these, if you imagine a perfect carbon diamond structure, you could dope in this way B, N, and B, and then that would be correspond to a perturbing Hamiltonian from the pristine carbon diamond. And if you apply the opposite sign of that perturbing Hamiltonian, you would get the NBBN. And according to the symmetry, then they up to third order, their electronic energy is the same. You can therefore view it like this, right? Similar to the N2 sitting on the ridge, you have now benzene, and these two alchemical enantiomers, they sit on two separate sides of this little hill here, and you dope twice. Of course, you also have other enantiomers, so the NB or the BN, right? They are trivially identical again due to rotation, and so these are not alchemical enantiomers, but you doped only once, so they are higher in energy than these twice doped guys. Now, if you presume that you perturb this system to include B and N, then you would find that B and N and N and B are the two possible ways, and this would lead you to one enantiomer and a neighbor. And so while these two enantiomers are very close to each other, up to third order exactly, this one is not very close, but it's still similar in energy, right? And so you can construct approximate equalities throughout chemical compound space, and you can use them to rank them approximately in terms of their total energy. And this is what you see now here. This is the alchemically estimated rank of all these anthracene doped systems. So you see blocks of stoichiometry. So this is if you dope everybody. Here you have 2 carbons left, and here you have 4 carbons left, and up here you have 6 carbons left. And then there's a very small number of compounds with 8 carbons left and only 1 BN. Right? And we estimated now the rank for all these molecules just based on benzene without a single quantum perturbation calculation. This is exclusively due to symmetry arguments. And you see that the estimated rank correlates very well with the actual QM rank, which you would obtain if you did the quantum calculation. We also, for comparison, have here a cumulative distribution for other methods. And you see that alchemy is certainly better than bond counting. And it's actually sort of close towards XTB calculations, which are already approximate quantum chemistry calculations. We further extended this to this scaffold here, and we ranked all possible dopants with these stoichiometries you see up here. So with 1 BN pair, 2 BN pairs, up to 11 BN pairs. We jumped some BN pairs between 6 and 10 because there were simply too many molecules. If you consider just these stoichiometries here, there are over 400 million doped mutants you could consider. And based on the symmetry arguments, again, we could rank them all in terms of their energy. And once you do this, you can, of course, look not only which ones are the most stable ones and the least stable, which is something we have included in this paper, but you can also look how do structural descriptors correlate with these trends. And for instance, if you count the BN bonds, right, per BN pair, right? How many BN bonds, direct BN bonds? So how close are the boron and the nitrogen atoms? Then you find a clear correlation. The closer they are for this stoichiometry, right, but also for the others, the closer they are, the more you have that are close, the lower your energy. Okay. So these are the lowest in energy, and they have many direct BN bonds, and the least stable one in this stoichiometry has the least direct BN bonds in the scaffold. So you can extract structure property relationships very easily just by a symmetry argument, which does not require you to perform any quantum calculation. All right, with this, I'm at the end of this lecture. Are there any questions at this point in time? This doesn't seem to be the case, so I'd like to thank you all for your attention, and I'll see you next week then for the next chapter on machine learning for the purpose of this course. Thank you so much, and bye-bye.
Bye.
Bye.